Greetings everyone, and welcome to the Cart Moving Down an Incline pre-lab. So in this unit, we're going to start out by looking at the motion of a cart as it rolls down an incline. And we're going to want to try to compare the motion of this cart to the motion that we saw of the toy car a couple of units ago. See if it's a different kind of motion, and if so, how we can represent it. So, first of all, let's take a look at this kind of cartoon cart, which matches the motion you see with a actual cart rolling down the incline. Watch the motion and see how it compares to the constant velocity toy car. Don't know why I made it explode, just something I could do with PowerPoint. So, what did you notice about the car? Did it move with constant velocity like the toy car did? No, it was speeding up. Here it goes again, just to show you. So notice here, it's getting faster and faster as it goes down. This is different than we looked at with Newton's first law, when we were mainly looking at constant velocities. Now, we do actually have enough physics to understand why this cart sped up as it went down the incline. Let's do a little force diagram on the cart. Okay, now we're going to rotate our axes so that our x-axis is right along the incline, parallel to the incline, because that way we make the motion one-dimensional, if you remember. Now the motion is up and down the incline, the x-axis, rather than being horizontal and vertical at the same time. So it's going to make our equations and things we're eventually going to do much easier if we rotate our axes. So, what forces act on the cart? Well, of course, it interacts with the Earth, and therefore there is a force of gravity which acts straight down. Since we've rotated our axes, the force of gravity is no longer along an axis, so we must break it up. We must resolve it into its perpendicular components. So there is the part of the force of gravity which acts perpendicular to the incline, F of gy. And there is the component of the force of gravity which acts parallel to the incline, F of gx. Notice here, F of gx and F of gy are perpendicular to one another. This little right triangle vector diagram, F of g is the hypotenuse. And hopefully you're drawing it right. Now, as we showed last unit, when you rotate the axes to make your x-axis parallel to the incline, your angle of inclination ends up right there as the vertex angle in your vector diagram. Now, the cart is also being supported by the incline, so that would be a normal force. But in this case, the normal force doesn't act straight up. Remember that normal means perpendicular to the surfaces. That's what it means mathematically. So therefore, the normal force acts along the y-axis. So we don't need to break it up. Now, that's it. The cart is only interacting with the incline and with the Earth. There's no person pushing on it. There's no frictional effects, as we're assuming here the wheels are perfect. There's no tension or string or spring or anything like that attached to it. So let's look at these forces now. In the diagram, you can see that F of n and F of gy are balanced. You have to cancel out. Why? Well, because the cart is moving down the incline. It's not moving at all perpendicular to the incline. That's why we rotated the axes. And of course, if something isn't moving, it's moving at constant velocity. And Newton's first law says, constant velocity, no net force. Forces must balance. But while we've balanced this part of the force of gravity with the normal force, F of gx is sitting all out here by itself. There's no friction to balance it, there's no applied force to balance it, and therefore it is an unbalanced force. And again, by Newton's first law, what do unbalanced forces or net forces do? They make things change their velocity. And since the unbalanced force is pushing down the incline and the cart's moving down the incline, it's going to make it speed up. So this is why the cart speeds up as it goes down the incline, because there's an unbalanced component of the force of gravity. Now, since this cart is moving and we want to examine its motion, much like we did with the toy car, we're going to use the same two variables. We're going to measure the position and the time for the cart as it rolls down the incline. And therefore, the purpose of this lab is to create graphical and mathematical representations of the relationship between the position and the time for a cart moving down a frictionless incline. Now, in this case, we're not going to be able to do the lab like we did with the toy car lab. Remember the toy car lab, we waited every 3 seconds, we put a block down, and then we measured how far away that block was. That's not going to work in this case because with the carts and tracks we have in the back of the room, it takes a second or many times less than a second to roll down the incline. So instead, we're going to kind of do this lab backwards. We're going to choose positions, okay? And we can do that with these photo gates that you see, which we'll talk a little bit about here. And there's a scale already right on the track. And then we're going to use the photo gates to measure the amount of time it takes to roll to that position. And the photo gates are going to help us do this very precisely. Okay, it'll be a little program which, when opened, it'll just be a box which will say time between photo gates. Right? And so when you hit start and let the cart go through, right, the picket fence on top interrupts the photo gate, starts the timer. When it interrupts the bottom photo gate, it stops the timer and very precisely measures it. So no need for a stopwatch and all that human reaction time error. Now, one little thing. When we get all this data, we're going to want to graph it. Our rule of thumb has always been to put the independent variable on the horizontal axis. But that would mean we'd have graphs of time versus position. And that's not something that we've dealt with before. So we're going to violate our rule of thumb. We're going to graph it as a position versus time. So just like the graphs that we made in the constant velocity unit, we're going to put position in centimeters on the vertical axis and time in seconds on the horizontal. Now, why would we want to violate that rule of thumb? Well, because we want to understand what the graph means, and all of the meanings that we developed were all based on position versus time graphs. For example, we know that the slope of a position versus time graph is the velocity. It tells you what direction and how fast you're moving. We know that the y-intercept on a position versus time graph is the initial position, your starting place. Right? So we want those meanings to still hold. We want the steeper the slope, the faster it goes. All the things that we learned when we were doing constant velocity. So, a couple of things that are going to help your lab work a little better. First of all, the Data Studio file, which is on the shared drive in the normal place, is called Cart on Incline. It's under Unit 2, Data Studio files. And when you open it up again, it'll just have a big box. Don't change the size of the box, just leave it alone. All right, and you hit start. Cart interrupts the top photo gate, starts the timer, interrupts the bottom photo gate, stops the timer. A very precise time pops up. That's the time between the photo gates. You write it in your data table. All the tracks are inclined as close as I could make them at 10 degrees, so don't change the tracks. Don't move them, especially don't change the angles with them. Now, the high photo gate, if you look at the downhill edge of it, it will be set right at 10 centimeters so that we have a place to measure from. We're always going to measure the downhill side of the bracket, downhill edge of the bracket. We're going to move the lower bracket up and down the incline, which will change the position. And again, we'll measure from the 10 centimeter mark, and we'll measure to the downhill edge of the lower photo gate. Now, here's a tricky one. I want to have a 0, 0 point on this graph to make it a little easier to interpret. So to do that, I need the timer to start as soon as the cart starts to move. The only way to do that is to start the cart as close as you can to the top photo gate. Now, how are you going to do that? Well, the photo gates have these little red lights on top, and the little red lights turn on when the photo gate is being interrupted. So I would suggest rolling the cart into the photo gate so that it's interrupting it, and then rolling it till it just turns the light off. That means that the cart is just out of the photo gate. Don't put it 3 centimeters up the hill. I mean, really work at trying to get it to be right when the light turns off. Somebody hits start. You don't have to worry about getting the start at the same time you drop the photo gate or drop the car, let the car go. It doesn't work that way, all right? It doesn't start timing till the cart goes through the photo gate. Somebody hits start, you let the car go, goes through the 2 photo gates. Please catch it at the bottom. Time's there. Okay, you can run another trial. Remember that Alt- is the quickest way to delete a trial. When you get done with this graph, it's going to look a little different than the constant velocity position time graphs did. Remember, since slope was the velocity, constant velocity had straight line position time graphs. Well, this isn't a constant velocity. This is speeding up. And so we're going to end up with a curve. Now, it's going to be a kind of curve that we've seen before. And so you know that when we have a curve, we need to do the process called linearization. And so when you're in the back and you're graphing with LoggerPro, you're going to want to linearize your original graph. If you've forgotten how to do that, check the laminated sheet by the computer, and when it's all done, call me over to look at it before you sketch it out on your data sheet, because I need to make sure it's okay and the slope is okay and all that kind of stuff. So have fun with the equipment, but please, it's expensive and precise. So make sure you're catching the cart before it hits the bottom of the track, because I really don't want it to smack into the bottom. Thank you.